a recording. Okay, all right, so let's go ahead and move on to 1.3, exponential functions. Exponential functions. Okay, this is really also kind of, we already did all this stuff, but let's review it. Exponential functions, y is equal to a to the x. This is an exponential function. Exponential function looks like this. An exponential function can be either a growth or a decay function. What determines whether it's a growth or a decay? Anybody? Spit it out.
If it's negative or not.
Nope. Nice try. Thanks for playing. Next. Okay, what determines whether it's a growth or a decay is the A, right? The base. In other words, if you are like this is a growth. If you are like this, it's a decay, right? In other words, if A is between 0 and 1, in other words, if it's less than 1, it is a decay function. You're going to decay away. If you are greater than 1, you're going to grow, which makes sense, right? If you are growing 10% a year, you end up putting, what is my A for that? Does anybody tell me? What would be the base if I am growing 10% per year? What happened? Everybody forgot about this? It's going to be 10%, right? So it's going to be 1.10% to the x, so it's going to be 1.1 to the x. So the bottom is greater than 1, so it's going to be a growth function. If I am decreasing by 10%, it's going to be 1 minus 0.1 to the x, makes it 0.9 to the x, correct? Are we good with that? Are we all good? This kind of ring a bell, I hope. All right, okay, all right. So we're, oh, Logan decided to join us. Okay. So that's that. Let's look at example number 1. Graph the function, state the domain and the range. Okay, so let's look at the function itself. I'm not going to do example 1, but let's look at an exponential function. And you can tell me what. So a growth function is going to look like this, and it's going to go through what point is this point right here? Anybody tell me what that point is? Where does it go across the y-axis called the, what? The y-intercept is 1, right? Y is y-intercept when x is equal to 0, and x is equal to 0, y is equal to e to the 0 is going to be 1, right? Anything to the 0 power is 1. So it's always going to go through this point right here, 1, right? Okay. So the domain is what? What is the domain? Luke, what's the domain?
Greater than 1, greater than 0?
Nope.
Oh, the domain?
The domain, all possible
All real
x's.
numbers.
What?
All real numbers?
All real numbers, correct. That's right. The range, you were trying to find the range. What is the range then, Luke?
Greater than 0?
Greater than 0, right? So y is going to be greater than 0. It can't be 0, right? Because it's never going to quite go to 0, right? That's why this is called an asymptote, right? It's not going to go 0, but it's going to try to get there. So it's going to be y is greater than 0 would be the range, right? The domain and the range there. Okay, all right. Let's do example number 2. Find the zeros of f of that. Let's say do it graphically. So by the way, so this is a growth. A decay is going to look like this, right? A decay is going to look like this, all right? But it still has the same domain and range. The domain, all possible x's, is all reals, right? And y-wise, it has to be greater than 0, so it's going to look like that, right? Okay. Example number 2, we have find the zeros graphically. F of x is equal to, example number 2. f of x is equal to 5 minus 2.5 to the x, 2.5 to the, not 0, but x. And to find this graphically, you would just go ahead and plot it, and you would trace it and find the zeros, right? It's pretty simple enough. If I ask you to do this, if I ask you to solve this algebraically, how would I go about doing that? Anybody tell me how I do that? Eva, any thoughts on this?
I have no idea how you do it alphabetically.
Okay, so you would move it over, right? First of all, you get 5 is equal to 2.5 to the x, right? So what is the problem here? I have the unknown is in the exponent, correct? So somehow I need to get that exponent down out of the exponent part, right? So how would I do that? What kind of function allows me to do that?
Can you like log it?
Take the log, right? You would take the log, right? So you would log, natural log of 5 is going to be equal to the natural log of 2.5 to the x. The laws of the law of the logs say now this comes down to the forward. So this becomes x. Now it's off, x is going to be equal to natural log of 5 divided by natural log of 2.5, right? You can also do common log, the same thing, right? Common log, I can do the common log, the same thing. I can do the common logs, right? But, or the 10 base logs, or I can do the natural logs here. It doesn't really matter, okay? But this is how you would do it algebraically. Okay? All right. Middle of page 24, there's a green box that says rules for exponents. Go ahead and briefly look at that for me. Any questions there? Anything we need to go over? Anything that does not ring a bell? That looks weird? No? Okay, so moving on to exponential decay. Exponential decay. Exponential functions can also model phenomena that produce a decrease over time, such as it happens with radioactive decay. Okay, radioactive decay in particular, we use what is called a half-life. We use what is called a half-life, right? This would be the symbol that you see. I think this is actually on the game itself too. If you ever played the computer game Half-Life. The rate of a radioactive something is the amount takes. So this is the half-life is the amount of time it takes for a substance to decay away and only have half of its original amount left over. Okay, so let's jump right into the example. Suppose the half-life of a certain radioactive substance is 20 days and that there are 5 grams present initially. Then when will there only be 1 gram of this substance remaining? Okay. So the function is going to look like this. F of x is going to be equal to the initial amount of what's there. And then in every half-life, it's going to go like this, right? As time goes by, it'll go line like that. So now here's the thing that kind of confuses you. You're going to say, well, you know, sometimes in some books you will see that t up here written as t divided by 1 half-life, okay? And this actually gives you the number of half-lives, okay? And here we're asking for what? They were not asking for that, right? We're asking for just the time. How much time will be when there's only 1 gram limit? So we're not looking for this. We're looking for the time, right? We're looking for just the time. Okay, so on this one, the initial amount was how much? 5 grams. So I'm going to have 5 grams here is going to be equal to, what? 5 grams is going to be equal to 1/2 times t, and this is going to be, after a certain amount of time, there's only going to be 1 gram left. So this is what we need to find, right? So again, we would do what we just did with the logs, right? We would solve this by, this is example number 3. Example number 3. So we do the same thing. We divide each side by 5. I get 0.2 is equal to 0.5 to the t. This is what we're looking for. Okay? So we would solve this by, again, taking the log of both sides. So I'm going to get log of 0.2 is going to be equal to log of 0.5 to the t, where the t now comes down over here. The t's go away. T is going to be equal to log of 0.2 over log of 0.5. And that's your answer. Okay, so that's how you would solve that. Okay, or you can actually, the book I think just allows you to just go and do it graphically. Okay, you can do it graphically also, obviously, right? So go to the top of page 25. It shows the definitions of exponential growth, exponential decay. Okay, the function y is equal to k times a to the x. This is growth if a is greater than 1. Decay if it's a is greater than, less than 1, but greater than 0. Okay? So that's that. We're going to go ahead and call it a half at this point, I think. So let's go ahead and have you start working on the homework. And we'll go ahead and pick back up where it says compound interest. So I'm going to stop. Where am I at? Stop.